2 words, quantum physics. We're gonna go there in this episode of the Cool Parts Show.
Thank you, Carpenter Additive, sponsor of the Cool Parts Show Season 2. How do you inspect additive manufactured parts? Lots of ways. Stick around to the end of the episode. We're going to complete our tour of the Emerging Technology Center in Athens, Alabama. Now back to the show. I'm Pete.
I'm Stephanie.
We are with additivemanufacturing.media.
And this is the Cool Parts Show, our video series where we talk about cool, weird, and unusual 3D printed parts.
Okay, weird and unusual. So that's what I'm seeing here. This has got to be the weirdest looking cool part that we've ever discussed. I'm excited to learn about this. What is this thing?
Okay, so this is an ultra-high vacuum chamber to contain a cloud of atoms used in quantum physics research.
Okay.
So this was built as part of a feasibility study by a company called Added Scientific. They're in the UK. And obviously, I'm not a quantum physicist, so I want to bring in someone who is also not a quantum physicist, but he is the engineer who designed this chamber. So this is Lawrence Coles at Added Scientific explaining in a little bit more detail what this part is all about.
This is a ultra-high vacuum chamber that we've produced using additive manufacturing. It's the world's first ultra-high vacuum chamber that reaches times 10 to the minus 10 millibar range. And it's used in the quantum technology sector. And for this particular application, it's used to trap cold atoms at its core using laser cooling and also magnetic fields. And with this type of chamber, we can produce atomic clocks, garimeters, applications that might help with communication, quantum positioning systems, and other quantum-based technologies.
Okay, so we talk about how weird this part looks. Maybe the weirdest, most visible thing is this particular wavy, warpy, kind of like a sponge lattice form, right? What is that?
Yeah, so one of the things that Lawrence mentioned is cooling. So these chambers keep the atoms really, really cold, like close to absolute zero, so that they kind of condense into this cloud. And so part of the function of these lattices is to help with heat dissipation, to help maintain that cold temperature. But the weird gyroid pattern that you're seeing comes from a proprietary software program that Added Scientific has developed to create designs like this.
Okay, so that gyroid, so that's an example of a shape, a surface shape complexity you could only get through additive manufacturing. So let's talk about that. What is the additive process that produced this?
So this was built on a Renishaw AM250 laser-based powder bed fusion. We've talked about that before. The engineer who built it, her name is Sarah Everton. And this part was printed initially, and then it had to go through a couple of post-processing steps, so a few rounds of heat treatment, and then finish machining for these shiny faces that you see.
Okay, so that's how it was made. What's it made of? What's the material?
Right, so this is an aluminum alloy. It's aluminum silicon 10 magnesium. And that's a good question because when you have an ultra-high vacuum chamber like this, actually the material is really important. You have to really understand how it's going to behave in these conditions.
During the development of this chamber, we've characterized this aluminium alloy in terms of its outgassing properties. And during the application in ultra-high vacuum, various contaminants and parts of the alloy itself can outgas into the environment inside the chamber. And by studying this material within this environment, we begin to understand how this material behaves when it's subjected to the ultra-high vacuum, and that's something that's very important for this application, is this further characterization of the aluminium alloy beyond that of mechanical testing.
Okay, so the outgassing, like I'm really fascinated with that. So the pull of the vacuum is so strong that it can draw stuff out of the surface of the metal.
Right, and that stuff can kind of contaminate your cloud of atoms, right? So conventionally, a chamber like this would probably be machined out of stainless steel. And it's not because stainless steel doesn't have that behavior. Just about any material would outgas under ultra-high vacuum conditions. But it's because we really, we understand very well the behavior of stainless steel in those conditions.
Right, so they're now trying to understand the same thing about this material, this aluminum alloy.
Right, yeah, understanding the material, understanding the 3D printed material, and they made a couple of choices to kind of help characterize the aluminum alloy a little bit better. So one of which is, if you look at the inside of the chamber, it's still got this rough printed surface. And there were concerns that a rough surface would outgas more than a smooth surface. And so to test that, they left it this way. But they actually found in doing experiments with this that the rough surface performed actually a lot better than they expected.
Okay, so here's what really strikes me about this. We're talking about outgassing, we're talking about this behavior under vacuum. There was a time when the question about additive manufacturing was, can 3D printing in metal give you a quality part, the same kind of quality we expect of other processes, casting, forging? A concern not long ago was porosity, right? The density, the integrity of the metal. It is apparently the case that concern has utterly been overcome, because here's a part that is expected to hold a vacuum so well that it can isolate atoms, individual atoms, for quantum physics research.
Right, and so, you know, even just a couple of years ago, holding the vacuum might have been the concern, but powder bed fusion has progressed to the point where it's reliable, but even more than that, it's controllable enough that we can print a chamber like this and be pretty confident it's going to hold the vacuum. So what this feasibility study was all about was not so much a test of 3D printing as it was a test of the material.
Okay, what else should we know about this part?
Well, so we talked about the material, and we should say that aluminum is going to be lighter than stainless steel. And we talked about this lattice pattern. And the combination of those two things means that this vacuum chamber is actually a lot lighter than a conventional chamber.
All right.
It's only about 245 grams, and that's about a 70% weight reduction over a stainless steel chamber made conventionally of about the same size.
Okay, lightweighting, yes, advantage of additive manufacturing, but I think about lightweighting in terms of like aircraft parts or even auto parts. Why is a lighter vacuum chamber important? How does that help?
So I think Sarah explained it really well in an email. She called this chamber the heart of a quantum system. So if your chamber is really heavy and awkward and difficult to move, it's going to limit your research possibilities. You're not going to be able to use it in as many places in as many ways, and it would limit, you know, the kind of devices you could put this into.
Yeah. So wow, we're in this conversation, we're ticking off all these different additive manufacturing advantages. Right? There's the design freedom, there is improved cooling, there is lightweighting. And so if we continue on that list, I would get to assembly consolidation. Is that going to play a role here?
Yeah, so for this feasibility study, they wanted to be able to use off-the-shelf components with this system. So that's why it's the size that it is, so that it can mate with all of these other existing parts. But what you're hinting at is something that, yeah, they're going to be looking at in the future. So here's Lawrence again to describe the potential there.
The next development for us is to take this chamber developed for the feasibility study and to look at the wider vacuum system in the various quantum technologies, and to look at consolidating parts, reducing the assembly, reducing the size of the assembly, the weight of the assembly, and then overall the power of the assembly, and to also add in a lot of extra exciting features that we have planned coming up next.
All right, I think I got this. Vacuum chamber. Holds a vacuum for quantum physics research, isolates a cloud of atoms within this vacuum. This lattice for cooling. Cooling is very important to maintaining that vacuum. This lattice makes it more effective. A different material choice, an aluminum alloy, makes this part lighter. But what that requires them to do is test the behavior of this material under vacuum, test it for the outgassing effect. Strikingly, this feasibility study is not a test of the feasibility of additive manufacturing. That's solid. It's a test of this material, and can they use this lightweight material to make this more complex, more effective form.
Yeah, so that's a great summary. One other thing to point out here is that, quantum physics researchers, whether they know it or not, have kind of been limited by their equipment. There's only so many possibilities with existing vacuum chambers. And so something that Lawrence is really excited about is the opportunity to talk to these researchers about, okay, what is it that you're really trying to learn? What kind of tools do you really need? And be able to develop chambers that are going to be purpose-built for the experiments that they want to run.
Let me tell you what that makes me think about. So like we look at season 2, the cool parts we've covered, and they've been what? They've been an auto part, a part of a motor. It was a motor for a drone, but it's still a recognizable engine part. Glasses, the glasses you're wearing, an orthodontic mouth guard. All throughout season 2, we've seen how additive manufacturing is affecting everyday objects we recognize, and the transformation there is powerful and profound. But beyond that, here's this application I wasn't aware of, and even after this talk, I don't completely understand it. Quantum physics research. The possibilities available to quantum physics researchers are now expanded and taken farther because of additive manufacturing, because of this new disruptive manufacturing process. And that leaves me wondering, like, just how far will the impact of 3D printing go? How many different sectors and realms and worlds and fields of pursuit are there that are going to have new possibilities because of the special cool parts in their worlds?
Yeah, I don't know, but I really hope that we're going to find more of those in season 3.
Yeah.
So that's a wrap on this episode and this season of the Cool Parts Show. If you want to learn more about this vacuum chamber, you can find a link to our article in the show notes or at additivemanufacturing.media.
Email us if you might like to see your cool part featured, maybe in season 3, coolparts@additivemanufacturing.media.
If you like the show, be sure to subscribe. You'll be the first to know when season 3 drops. Thank you for watching.
Thanks so much. I'm at Carpenter Additive's Emerging Technology Center in Athens, Alabama, contract additive production facility. But production isn't done until measurement validates the part has been made to spec. Carpenter has every measurement tool it might need to perform that validation. Maybe most significantly of all, CT scanner for evaluating the inside of an additive part. Why so many measurement tools? It's because additive manufacturing is a special process.
So printing is just one step in the whole process chain, and each of these steps can be very labor intensive, very time consuming. So we need to make sure that we're catching deviations or non-conformances at every step of that, so that it doesn't propagate down and cause us an issue at the very end. When we catch those deviations, there are a couple of things that can happen. We can either rework that part and get it back into the standard flow, or in the worst case, we have to scrap that and start again. Additive is such a relatively new fabrication technique, so we don't have all of the statistical data that some of our other fabrication techniques have. I fully expect as we get more data around the material's performance, we're going to require less and less actual in-process inspection as we get better at predicting the outcomes, as we get better at identifying deviations in real time.